Hello and welcome to this video about heterocyclic chemistry. In this video we'll be talking about some general and miscellaneous reactivity of heterocyclic systems, including the lithiation of heterocycles and the deprotonation of heterocycles, the reduction and oxidation of heterocycles, and some cycloadditions and rearrangements. So, to start off with, if we treat 5-membered heterocycles with strong lithium bases, we can incorporate a lithium on the heterocyclic ring. This is really useful because then they become good nucleophiles. Now, in the case of all these different heterocycles, you'll see something in common. The position the lithium ends up at, here indicated with the grey arrows, is always the 2 position, or the position next to the electronegative atom. This is because this gives the best inductive stabilization through the sigma framework. The electronegative atom can stabilize that negative charge. And so we can remove one hydrogen from all of these heterocycles to give us a really useful lithium nucleophile. An example of this is if we take this hydroxymethylfuran. Now here we're going to need 2 equivalents of butyl lithium. The first equivalent will remove the acidic OH proton. Then the second equivalent selectively removes the proton next to that electronegative atom, so that if we introduce an electrophile such as formaldehyde, now the second deprotonation becomes the most reactive part of that molecule because it's the highest in energy, because it's the hardest to get to, and therefore that's the one that attacks first to our electrophile, makes a new carbon-carbon bond. The resulting product can be worked up using water or ammonium chloride to give us the new symmetrical product. So if we look at that in detail, our start material is hydroxymethylfuran. We're going to use 2 equivalents of butyl lithium base. The first equivalent will remove the most acidic proton, which is our OH. And the second equivalent will remove the second most acidic proton, which is the one on our heterocycle. This turns our heterocycle into a really good nucleophile. So we introduce some electrophiles such as formaldehyde. We get attack of the formaldehyde and formation of a new carbon-carbon bond. The most reactive nucleophile is the last one formed because that was the hardest to form. So we get attack of the carbon to make a new carbon-carbon bond to give us our symmetrical product. And when we work this up with a source of acid such as ammonium chloride, then we get the product with 2 OH groups. However, when we move to 6-membered heterocycles, we can't deprotonate those in the same way with strong lithium bases. And that's because we've seen that these are good nucleophiles. So instead of removing the proton, they will attack to break the ring and put that stable negative charge onto the nitrogen atom. Therefore, if we want to get the same kind of lithiated species with a pyridine, then you're going to have to start off with the corresponding chloride and do lithium halogen exchange instead of deprotonation. One other alternative to fade the lithiation is to use a directing group. With a careful choice of a group, such as an amide, you can force lithium to be a good base. The way this works is that the electron lone pair in the amide, which is boosted because of the nitrogen lone pair, pushes into the system, can coordinate to lithium, which means that when we lithiate in the position shown here, that's more stable because we have a more stable neighbouring group, oxygen, to stabilise it. Then again, this could be a good nucleophile for further reaction. If we look at this a little bit more slowly, we have our directing group, which is a bulky amide. Bulky amide so we don't just get direct attack of the carbonyl, and to help our coordination. The base we're using in this reaction is lithium TMP, so tetramethylpiperidine. And we use this base because it's extremely hindered. It's like a very bulky version of LDA. So now what happens is lithium, which is a hard, positive charged metal cation, will coordinate to as many things as possible, including the oxygen lone pair on our amide. This will bring the base into close proximity to the proton on our pyridine ring. And therefore favour deprotonation at this position. This gives us the resulting lithiated intermediate, which could go on to react with other things, and the reason we get this lithium is this very stable 5-membered cyclic stabilization. So if we move a little bit further away from our 6-membered heterocycle, remembering that 6-membered heterocycles are electron poor, well, we can actually deprotonate next to the ring at the alpha positions. If we take 4-methylpyridine and treat that with LDA, you can see how we can draw the electrons moving around the ring to put the negative charge on the most electronegative nitrogen atom, which means it's a good nucleophile for further attack on something like an acid chloride. If we compare that with toluene that doesn't have the nitrogen in to help stabilize that negative charge, you'll see that the pKa is around about 10 times lower, which is a factor of over 1 billion times more favoured for the pyridine than the toluene. We can draw this in more detail. And this works best if it's a 2 or 4 substituent, because then when we have a base, we can draw a curly arrow mechanism that removes that proton and puts a resulting negative charge on our electronegative nitrogen atom. And we can do the same thing with a 4 substituted pyridine. Then when we put in an appropriate electrophile, we can make a new bond between the alpha position and our electrophile. So we take the negative charge, push that back in with our curly arrows. To give us the new bond. We can get the same reactivity on fused heterocycles. Their aromatic system is constructed in the same way, and we can see that here we have deprotonation alpha to an isoquinoline, followed by attack on an electrophilic carbonyl, and in this case we actually get elimination of water from the product to give us a conjugated system. So we've seen a lot of chemistry about aromatic heterocycles, and one of the things we can do is we can reduce aromatic heterocycles down to the corresponding saturated version. Now, to do this we do have to destroy the aromatic system, so you do need some quite harsh conditions. So for example, to reduce furan to tetrahydrofuran, we need Rayleigh nickel, which is a very reactive form of nickel. To reduce pyrrole down to pyrrolidine, we need platinum, which is a reactive precious metal. Now, thiophene is a little bit different. Because sulfur is the next row down in the periodic table, the aromatic system is not as stable. So in this case, we've got to be very careful. And we only want to add 2 equivalents of hydrogen, because if you add more than 2 equivalents of hydrogen, you end up reducing the carbon-sulfur bonds as well. Finally, this works on 6-membered rings as well, and by using Raney nickel, we can reduce pyridine to piperidine. We can also use metal hydrides to reduce pyridine systems. The pyridine is electron poor, so it reacts very well with something nucleophilic. But if we use something like lithium aluminium hydride that we've seen before, it gives a very complicated mixture of products. However, if we swap that for zinc hydride or magnesium hydride, then what we get is a conjugate addition all the way at the 4 position. No, we don't. What we get is attack at the 4 position. We push those arrows round to put the negative charge on the nitrogen, and that becomes a ligand for the zinc. So you end up with this species where you have a zinc coordinated to 4 different nitrogens, 2 of which are pyridines that have been reduced. If we want to go the other way, we want to oxidize our dihydropyridine up to our pyridine. Well then, there are many different reagents that do this. Standard reagents, metal reagents such as manganese-based oxidants will work. But one of the most common is DDQ. This is this organic molecule here with 2 carbonyls on the opposite end of a 6-membered ring. Now this is not aromatic, it's extremely electron poor. We've got electron withdrawing chlorides, ketones and nitrile groups on this ring, and so it readily accepts a hydride or an electron. So we can draw a mechanism whereby the lone pair of the hydrogen, the lone pair of the nitrogen comes in and pushes out one of the H's as an H- to make a new bond to the DDQ. And the driving force for this is that after the first step, the DDQ could tautomerize, and this gives us a completely aromatic diol species, which can remove the proton from our pyridine and give us that product. We start off with a dihydropyridine. In this case, it's a 1,4-dihydropyridine. The hydrogens have been added at the opposite side of the rings. And we have the DDQ. DDQ is very electron poor, and so we can push the electrons from that lone pair in the nitrogen around the ring, make a new hydrogen-carbon bond, and make that aromatic pyridine species. The resultant DDQ has the O-, which can remove the proton from our pyridine, and we can tautomerize the ketone at the top of the molecule to give us the pyridine that we wanted and this aromatic product, this diol, which is the driving force for this transformation. So one of the most interesting transformations that heterocycles can do is cycloadditions. So a quick recap on the Diels-Alder cycloaddition. The Diels-Alder cycloaddition is a reaction between a diene and an alkene. The 4 electrons in our diene combine with the 2 electrons in the alkene in the cycloaddition to make 2 new carbon-carbon bonds. However, for this to happen, the diene, shown here with the blue orbitals, must adopt this S-cis or C-shaped conformation. And if it can't access this conformation, we don't get the right overlap for the transformation and the reaction doesn't happen. But if we look at our heterocycles, what we can see is they do contain a diene locked in this reactive or S-cis or C conformations. And so heterocycles often undergo cycloaddition reactions very effectively. Here we can see furan undergoing a cycloaddition with this alkyne. We also get the same reaction if we use pyrrole. It doesn't have to be 5-membered heterocycles. We can see here this is a pyridone. It has that diene as part of the backbone locked in there. And this also undergoes a 4+2 cycloaddition. And this last example is really interesting because we get a 4+2 cycloaddition between an oxazole and an alkene. The resulting 6-membered ring has a strained oxygen across the middle, which can be eliminated, and then water can be left in the molecule to give us a pyridine. So this is a reaction that transforms an oxazole into a pyridine. If we look at these in a bit more detail, our Diels-Alder reaction is a reaction between a diene and a dienophile. It makes 2 new carbon-carbon bonds. It's a 4+2 cycloaddition, 4 electrons in our diene and 2 electrons in our alkene. But for this reaction to occur, for good overlap between our orbitals, we need those dienes to be locked on the same side in a C-shaped or an S-cis conformation. In pyrrole, we can see that the alkene is locked into the C-shaped reactive conformation for Diels-Alder. So if we add the dienophile, in this case this alkyne, we can draw the cycloaddition. The cycloaddition takes these nice arrows which go around in a circle. It doesn't matter which way round we draw those arrows. And that results in the formation of 2 new carbon-carbon bonds. And gives us this bicyclic product. If we look at an oxazole, such as the one shown here, and that's reacted with a dienophile, like this alkene, with an electron withdrawing group on it, we can draw our cycloaddition arrows. This makes 2 new carbon-carbon bonds. It gives us a 6-membered ring. But because we started with this oxazole, because we start with the oxazole, we end up with the oxygen bridging that ring, which is a strain system. But we can relieve the strain by doing an E1Cb reaction, so the acidic hydrogen next to our ester. We can show the electrons flowing back up into our withdrawing group. then coming back in and relieving the strain by eliminating the oxygen. Now this molecule has that OH, which looks like a good leaving group. And so we can use the nitrogen lone pair to help that OH leave as water. And then finally, aromatization by moving this hydrogen, deprotonation. Gives us the pyridine product. An interesting property of nitrogen-rich heterocycles, especially triazoles with certain substituents around the ring, is their propensity to undergo rearrangement. You can see here by pushing the electrons around the ring, we can go from a ring-closed triazole form to a ring-opened diazo form. Now, because the bonds can rotate, what we can see is in this process we can swap that nitrogen, which is in red, in and out of the ring. So this is known as the Dimoth rearrangement. And here we're just changing red for blue nitrogens. But if we look at an example that has different substituents on the nitrogens, you can see that on the left-hand side, the ring nitrogen, the triazole ring nitrogen, has a phenyl group on it. But if we heat this up, you get an equilibrium whereby we get ring opening, rearrangement, and ring closing, so that the phenyl group moves out of the ring. If we look at this in more detail, we can draw the mechanism for this Dimoth rearrangement by pushing arrows around the ring. So we'll start off by breaking the nitrogen-nitrogen single bond and putting the resulting charge on the carbon atom. This gives us an imine. We can do this by using that lone pair of the nitrogen to help push through, and that results in this triple bond now with a positive charge on the middle nitrogen, which is one way of drawing a diazo species. It can be more conveniently drawn by just N2. Now, if we have a system with different substituents, for example, if we have an aromatic, if we have a phenyl group on the nitrogen of the ring, and an NH2 on our nitrogen next to the ring, then under the conditions, under high temperature, we can again draw our ring opening reaction, where our arrows flow around the ring. This gives us our diazoimine. Just draw AR instead of drawing out the whole aromatic ring. But now the bond in the middle is a single bond. So we can tautomerize, move the hydrogen from one end of our N to the other. But because that bond is single, we can rotate around there, which means that we can now close our ring in the other direction. So we can draw the reverse of the arrows that we drew before. So starting off with O-, making a new NN bond and quenching that positive charge. To give us the triazole product, which has now had the two substituents swapped. So the ring is an NH, and the group next to the ring is an NH-PH. What is interesting though is when it's in the ring open form, essentially we have a molecule of nitrogen in there, and molecules that are nitrogen rich and can give off nitrogen are commonly used as explosives. So these molecules at the bottom of the page here have all been evaluated or noted as being explosive. So we've seen a range of different reactions generally with these heterocycles, including the lithiation and deprotonation of 5-membered and 6-membered heterocycles. We've seen a few methods of reduction and oxidation of heterocycles, and we finished off by looking at some cycloadditions and rearrangements. Thanks for watching. I'll see you next time.